All right, welcome. Today we are diving headfirst into something that sounds like science fiction but is very, very real. Quantum computing. We're talking about a technology that could literally solve problems we've always considered, well, impossible. Okay, just think about this for a second. What if your computer, instead of crunching through a problem one step at a time, could try out every single possible answer? All at the same time. I mean, every single one. That's not just a small upgrade, right? That is the fundamental world-changing promise of quantum computing. So, before we get into the wild how of it all, we really need to understand the why. I mean, the computers we have now are amazing, right? But for some of the biggest problems out there, they are slamming right into a wall, a hard computational wall. Here's a great way to picture it. Imagine a giant complex maze. A regular, or classical computer would solve it by trying one path, hitting a dead end, backing up, trying another, and so on. It's methodical, sure, but for a huge maze, it would take forever. A quantum computer, on the other hand, gets to explore all the paths simultaneously. It's like it can see every possibility at once. And this gets to the heart of the issue, what scientists call the exponential scaling problem. It sounds complicated, but the idea is simple. Some problems just get ridiculously complex really, really fast. Think about designing a new drug. You're trying to simulate a molecule. If you add just one more atom to that molecule, the difficulty doesn't just go up a little bit, it explodes, growing exponentially. It gets so big, so fast, that even our most powerful supercomputers just throw up their hands and give up. You want to know how big that wall is? Okay, get this. Let's talk about breaking a standard 256-bit encryption key. You know, the stuff that protects your bank account, your emails, everything. For a classical supercomputer to crack that, it would take, wait for it, longer than the entire age of the universe. I'm not kidding, over 13.8 billion years. So yeah, I think it's safe to say we need a totally new way of thinking. And that new approach, that new way of thinking, it all starts with one tiny, incredible thing, the quantum bit, or as everyone calls it, the qubit. This is the absolute cornerstone, the fundamental building block of this whole revolution. So what on earth is a qubit? Well, let's start with what you already know. Your phone, your laptop, they all use bits. Think of a bit as a light switch. It can be off, that's a 0, or it can be on, that's a 1. That's it. Simple, right? Now, a qubit is a whole different beast. It's not a light switch, it's more like a spinning coin. While that coin is spinning in the air, is it heads or is it tails? The answer is, it's kind of both. It exists in a weird fuzzy state of being both heads and tails at the very same time. That mind-bending spinning coin state has a name, superposition. It's this almost magical ability for a qubit to hold the value of 0, 1, and everything in between all at once. It only picks a side, so to speak, when we actually look at it, when we measure it. That's the moment the spinning coin lands and we see if it's heads or tails. Okay, now this is where the real power kicks in. This is the magic. One qubit can represent two states at once, 0 and 1. But if you add a second qubit, you don't get 3 states, you get 4 states. 2 qubits, 4 states. Add a third, you get 8 states. You see the pattern? The power doubles with every single qubit you add. It's not adding power, it's multiplying it. That is what exponential growth looks like, and it's the secret sauce of quantum computing. It's a tricky thing to visualize, I know. So physicists came up with a handy mental model called the Bloch Sphere. Just picture a globe. Let's say the North Pole is state 0 and the South Pole is state 1. Your classical bit can only be at one of those two exact spots. But a qubit can be pointing anywhere on the entire surface of that globe. Every single point on that sphere represents a unique mix of 0 and 1. It's a beautiful way to see just how much more information a qubit can hold. Okay, so we have superposition. That's already pretty strange, right? Well, buckle up, because the next rule of quantum mechanics is where things get truly weird. Some might even say spooky. And this weirdness is exactly what makes it so powerful. And I'm not the only one who thinks it's spooky. The one and only Albert Einstein found this next concept so bizarre, so counterintuitive, that he famously dubbed it spooky action at a distance. So what is this spooky action? It's called entanglement. And here's the best way to think about it. Imagine you have 2 magic twin coins. You entangle them, you give one to a friend and they fly to the other side of the galaxy. You flip your coin and it lands on heads. The incredible spooky part is that you know instantly, without a shadow of a doubt, that your friend's coin just landed on tails. It's like they're linked by an invisible thread. The state of one instantly tells you the state of the other, no matter how much space is between them. Their fates are intertwined. All right, so we've got superposition and this spooky entanglement. These are amazing, mind-bending ideas. But they're not just for chalkboards and thought experiments. This brings us to the big question. So what? What can we actually do with all this quantum power? What problems can we solve? Well, the list of potential breakthroughs is, frankly, staggering. We're talking about things like designing brand new life-saving drugs by perfectly simulating molecules in a way we never could before. Or think about logistics, finding the absolute most efficient route for thousands of delivery trucks, a problem that would choke any classical computer, solved in an instant. It's a double-edged sword for security, too. A quantum computer could crack the encryption we all rely on today, but it could also help us build the next generation of unbreakable quantum encryption. And of course, it could radically accelerate the training of AI and machine learning models. The list just goes on and on. Now, this whole quantum revolution didn't just pop up out of nowhere. It's been a long, fascinating journey, moving from a wild theoretical idea to something that's actually being built in labs right now. And it has kicked off this incredible global race for something called quantum supremacy. The story really starts back in 1982, when the legendary physicist Richard Feynman first floated the idea of a quantum computer. For a while, it was mostly theory. But then, in 1994, a huge step, a mathematician named Peter Shor developed an algorithm that proved, on paper, that a quantum computer could smash modern encryption. That got everyone's attention. Things really started to accelerate in 2016 when IBM did something amazing. They put a 5-qubit quantum computer on the cloud for anyone to use. And then came the big headline in 2019. Google announced they had achieved quantum supremacy. They claimed their machine solved a problem that would be practically impossible for even the biggest classical supercomputer. And just look at the pace of this progress. It's just incredible. We're going from IBM's 5 qubits in 2016 to Google's 53 qubits in just 3 years. And today, we're already seeing processors with hundreds of them. Now, remember what we said about exponential growth. The jump from 5 to 53 isn't a jump of 48. It's an absolutely colossal, mind-boggling leap in computational power. So this isn't just theory anymore. It's happening, and it is accelerating at a breakneck pace, which leaves us all with one massive, thrilling question to think about. As these incredible machines get more and more powerful, what currently impossible problem will be the first one to fall?